Hello children, let us start work, energy and power. First we will talk about kinetic energy. In our previous classes, we have studied about kinetic energy and the formula to calculate it. Suppose a particle having mass m is moving with velocity v. Then its kinetic energy is given by the formula k is equal to half mv square. Now we will talk about change in kinetic energy. Kinetic energy of a particle changes if its mass changes or its velocity changes or both of them change. Usually mass of a particle does not change, so its velocity should change. Change in velocity means either particle should accelerate or decelerate. This can happen in the presence of a force. So a force is necessary to change the kinetic energy of a particle. Let us talk about these 5 scenarios. In scenario 1, a particle is moving horizontally with velocity v. There is no force acting on it. That means its velocity will not change. So its kinetic energy will also remain the same. In scenario 2, a force is acting vertically downwards and particle is moving horizontally with velocity v. That means there is no horizontal component of force that can change the velocity. So velocity will remain the same in this case as well. So kinetic energy of this particle will also remain the same. In scenario 3, a force is acting on the particle at certain angle theta with the horizontal. That means this force can be resolved into two components, one horizontal, another vertical. Horizontal component of the force will change the velocity. So kinetic energy of this particle will change. In scenario 4, a particle is dropped from certain height h. Force of gravity on this particle will work vertically downwards and particle will also move downwards. That means force and velocity vectors are in same direction. So kinetic energy of this particle will increase. In scenario 5, a particle is projected vertically upwards. So it is moving upwards. Force of gravity on it will work vertically downwards. So force and velocity vectors are anti-parallel. So kinetic energy of this particle will decrease. Kinetic energy of a system of particles is the sum of the kinetic energy of all its constituent particles. It is given by k is equal to summation of half mi vi square. Kinetic energy k is equal to half mv square. If we differentiate k with respect to time, we get dk by dt is equal to d by dt of half mv square. Half m is constant, so it can be taken out. So right hand side will be 1 by 2m d by dt of v square. D by dt of v square is equal to 2v dv by dt. 2 gets cancelled. So right hand side will be mv dv by dt. dv by dt is acceleration a. So it will be mass into acceleration into velocity. Mass into acceleration is force. So it will be Ft into v, where Ft is resultant tangential force. Suppose resultant force F makes an angle theta with the velocity. So Ft will be equal to F cos theta. So we can put F cos theta here. So dk by dt is equal to F cos theta into v. That is Fv cos theta. We can write Fv cos theta as vector F dot vector v. Vector v can be written as dr by dt, where r is displacement vector. So dk is equal to F dot dr. F dot dr is called the work done by the force F on the particle during a small displacement dr. If we have to calculate the work done for a finite displacement, we need to integrate this. So W is equal to integration of F dot dr. F dot dr is equal to dk. So integration of F dot dr is equal to integration of dk. Integration of F dot dr is equal to W. So W is equal to integration of dk is k2 minus k1. That is change in kinetic energy. So we can conclude that the work done on a particle by the resultant force is equal to the change in the kinetic energy. This is called the work energy theorem. If F1, F2, F3 and so on are individual forces acting on a particle, then the resultant force F is equal to vector sum of individual forces. Then total work done W is equal to integration of F dot dr. In place of f, we can write f1 plus f2 plus f3 plus and so on. Now, this can be split as integration of f1 dot dr plus integration of f2 dot dr plus integration of f3 dot dr plus and so on. This can be written as w1, this can be written as w2, this can be written as w3 plus and so on. So, w is equal to w1 plus w2 plus w3 plus and so on. What it means is work done by the resultant force is equal to the sum of work done by the individual forces. Let us understand work done by a force. We will consider four scenarios: when force is constant, when force is variable, when force and velocity are perpendicular to each other, and when force is spring force. Scenario 1. When force is constant. We know that work done W is equal to integration of F dot dr. If F is constant, it can be taken out. So W is equal to F dot integration of dr, and integration of dr is equal to R. So W is equal to F dot R. Suppose force and displacement vectors make an angle theta with each other, then work done W is equal to Fr cos theta. We will consider three cases here. When theta is equal to 0 degrees, that means force and displacement vectors are in same direction. Then W is equal to Fr cos 0. Cos 0 is equal to 1. So W is equal to Fr. Work done is maximum in this case. When theta is equal to 90 degrees, that means force and displacement vectors are perpendicular to each other. Then W is equal to Fr cos 90. Value of cos 90 is equal to 0. So work done is 0 in this case. When theta is equal to 180 degrees, that means force and displacement vectors are opposite to each other. Then W is equal to minus Fr. That means work done is negative in this case. Consider a particle is moving along the straight line AB. Its mass is m and velocity is v. Force acting on it is gravitational force that works vertically downwards. Its component along the velocity or displacement is F cos theta. So work done by this force from point A to B is given by F cos theta into AB. This can be written as F into AB cos theta. F is equal to mg. In this right angle triangle ABC, AC is equal to AB cos theta and AC is equal to h. So in place of AB cos theta, we can write h. So work done in this case is, let's say, W1. So W1 is equal to mgh. Now consider the same particle is moving along the curve AQB. It is at Q. For a very small displacement dr, draw perpendiculars on AB. Let's say width of this strip is dx on AB. For a very small displacement, we can approximate this to be a rectangle so that dr is equal to dx. Work done in this case is given by W2 is equal to integration of F dot dr from Ri to Rf. Since F is constant, so it can be taken out. So W2 is equal to F dot integration of dx from A to B. And integration of dx from A to B is AB. So W2 is equal to F dot AB, and F dot AB is equal to F into AB cos theta. AB cos theta is equal to h, so W2 is equal to mgh. We notice that work done is same in both the cases. Now consider the particle is traveling back from B to A. So in similar way, we can prove that work done in that case will be minus mgh. Now we will draw two important conclusions from it. Conclusion number 1, work done by a constant force from A to B depends only on the positions of A and B and not on the actual path taken. We have already proved that particle has taken two different paths, but work done is same. Conclusion number 2. The work done by a constant force in a round trip is 0. That is, if a particle goes from A to B and then comes back to A, then net work done is 0. So in this example, if work done from A to B is mgh, then work done from B to A will be minus mgh. So net work done is 0. Scenario 2, when force is variable. Suppose force F is acting on a particle and it is getting displaced from position xi to xf. Force in terms of its displacement x is given by the formula Fx is equal to ax plus b Newton. We have to calculate the total work done by this force. So total work done W is equal to integration of Fx dx from xi to xf. In place of Fx, we will put ax plus b. So W is equal to integration of ax plus b dx from xi to xf. That comes out to be equal to a by 2 into xf square minus xi square plus b into xf minus xi. Suppose force displacement graph is given and we have to calculate the work done between x is equal to 0 to x is equal to 4 and between x is equal to 0 to x is equal to 5. Work done W is equal to integration of Fx dx from xi to xf. Integration of Fx dx is area enclosed between the curve and the x-axis. So work done between x is equal to 0 to x is equal to 4 will be area of this trapezium. We can divide this trapezium into one rectangle and one triangle. So work done in this case will be 30 joule. To calculate the work done between x is equal to 0 to x is equal to 5, we need to add the area of this trapezium and this triangle. Work done corresponding to this triangle will be negative as force is minus 6 Newton. So work done corresponding to this triangle will be minus 3 joule. So total work done between x is equal to 0 to x is equal to 5 will be 30 joule minus 3 joule, and that is 27 joule. Scenario 3. When force and velocity are perpendicular to each other. We know that work done W is equal to integration of F dot dr. In place of dr, we can write v dt as velocity v is equal to rate of change of displacement. So work done W is equal to integration of F dot v dt, and that is equal to 0. Since force and velocity vectors are perpendicular to each other, so their dot product will be 0. So work done in this scenario is 0. Scenario 4. Work done by a spring force. Consider a block is kept on a smooth table. It is connected with a light spring whose other end is attached to a wall. This spring block system is in equilibrium. Suppose the block is at x is equal to 0. Now a horizontal force F is applied on the block so that the spring is elongated. Let's say block is at x is equal to x1 now. Since the spring is elongated in forward direction, so force on the spring will work in opposite direction as per Hooke's law, and it is given by F is equal to minus kx. So work done by the spring force will be equal to integration of F dot dr. F is equal to minus kx. So W is equal to integration of minus kx dx from x is equal to 0 to x is equal to x1. Minus k is constant, so it can be taken out. So W is equal to minus k into integration of x dx from x is equal to 0 to x is equal to x1. So W comes out to be equal to minus 1 by 2k x1 square. Now consider the block moves from x is equal to x1 to x is equal to x2. So limits of integration will be x1 to x2. So W comes out to be 1 by 2k x1 square minus x2 square. You need to remember this formula. In figure 1, spring block system is in equilibrium. Let's say block is at x is equal to 0. This is our reference line. Movement of block and spring towards the right side of reference line will be considered positive and towards the left side will be considered negative. In this figure, block is pushed towards the wall so that spring is compressed. In third figure, block is pulled away from the wall so that spring is elongated. In this table, we have calculated the work done by a spring force in different cases of initial and final states of the spring. For example, in case 1, initial state of the spring is natural. So x1 is equal to 0. And final state of the spring is compressed. So x2 is equal to minus x. Putting the values of x1 and x2 in this formula, W is equal to minus 1 by 2 kx square. Similarly, we can calculate the work done in different cases. Before we talk about potential energy, let us see conservative and non-conservative forces. We can divide internal forces of a system into two categories. conservative and non-conservative forces. We can define them in two ways. One, if the work done by a force during a round trip of a system is always zero, the force is said to be conservative, otherwise non-conservative. And second, if the work done by a force depends only on the initial and final states and not on the path taken, then the force is called as conservative, otherwise non-conservative. For example, gravitational force, electrostatic force and spring force are conservative forces, as the work done by them during a round trip of a system is always zero, whereas friction force and viscous drag of a fluid are non-conservative forces, as the work done by them during a round trip of a system is negative, not zero. A conservative force is a function of position only, not velocity or time, whereas a non-conservative force is a function of velocity. It acts in the opposite direction of the velocity. Now let us talk about potential energy. In our previous classes, we have studied that the energy possessed by a body by the virtue of its position in a system relative to others is called potential energy. An object's potential energy depends on its physical properties and the position in a system. As we had started kinetic energy with change in kinetic energy, we will start potential energy with change in potential energy. We consider internal forces and external forces working on a system. Internal forces are divided into two categories, conservative forces and non-conservative forces. Corresponding to each conservative force, we associate potential energy, but we cannot associate potential energy corresponding to non-conservative forces. We associate kinetic energy with the external forces. So we define the change in potential energy of a system corresponding to a conservative internal force as UF minus UI is equal to minus W, or delta U is equal to minus W. Potential energy is represented by capital U. Here W is the work done by the internal forces on the system as the system passes from the initial configuration I to final configuration F. You need to remember this formula. Suppose only conservative internal forces work between the parts of a system and the potential energy U is defined corresponding to these forces. There are no external forces or the work done by them is equal to zero. That means these are the conditions. Conservative forces work, non-conservative forces do not work. External forces do not work, or even if they work, sum of work done by them is equal to 0. Then we can say UF minus UI is equal to minus W. That means change in potential energy is equal to negative of work done. From work energy theorem, replace W by Kf minus Ki. So UF plus Kf is equal to UI plus Ki. Sum of kinetic energy and potential energy is known as total mechanical energy of the system. From this equation, total mechanical energy final is equal to total mechanical energy initial. That means total mechanical energy of a system remains constant if these conditions are met by the system. This is known as principle of conservation of energy. In other words, we can apply principle of conservation of energy when system meets these conditions. The total mechanical energy K plus U is not constant if the non-conservative forces such as friction acts between the parts of the system. We cannot apply principle of conservation of energy in the presence of non-conservative forces. That means if this is strict, we cannot apply principle of conservation of energy. However, work energy theorem is still valid in the presence of non-conservative forces. As per work energy theorem, work done by all the forces, internal as well as external forces, equals the change in the kinetic energy of the system. That means WC plus WNC plus W external is equal to Kf minus Ki. Here WC means work done by conservative forces. WNC means work done by non-conservative forces. W external is work done by external forces. Kf is final kinetic energy of the system and Ki is initial kinetic energy of the system. Put WC is equal to minus UF minus UI. We know that UF minus UI is equal to minus WC. Change in potential energy of the system is equal to negative of work done by conservative forces. So putting this value of WC in this equation, we get WNC plus W external is equal to EF minus EI. That means work done by non-conservative forces plus work done by external forces is equal to final mechanical energy of the system minus initial mechanical energy of the system. Now consider these conditions. Conservative forces work, non-conservative forces do not work, external forces work, and sum of work done by them is non-zero. Then WNC is equal to 0 or W external is equal to EF minus EI. That means work done by the external forces equals the change in mechanical energy of the system. Now let us see gravitational potential energy. Suppose a block of mass m is kept on the ground. Then it is raised vertically upwards through a height h. We can consider the block and earth as a system. Gravitational force working between the block and earth is conservative. So we can associate a potential energy corresponding to this force. Gravitational force on the block is working vertically downwards and it is raised vertically upwards. So work done by the gravitational force will be negative. And it is given by W is equal to minus force into displacement. Force is equal to mg and displacement is h. So W is equal to minus mgh. Change in potential energy of the block earth system is equal to negative of work done by the conservative force. Put W is equal to minus mgh. So delta U is equal to plus mgh. That is, potential energy of block earth system in this case will increase. Similarly, if the block descends through a height h, work done will be positive and change in potential energy will be negative. That is, potential energy of block earth system in this case will decrease. Now let us see potential energy of a compressed or extended spring. Suppose one end of a massless spring is attached to the wall and other end is connected to a block of mass m. Now this block is pulled towards right through a distance x, so that the spring is elongated by a length x. Now in this situation, the spring will pull the wall towards right and pull the block towards left. As a reaction force, wall will pull the spring towards left and block will pull the spring towards right. These two are external forces. Work done by this force is equal to 0 because the point of application of force is fixed, and work done by this force is equal to integration of kx dx from 0 to x, and that is equal to 1 by 2 kx square. So total work done on the spring by external forces is equal to 1 by 2 kx square. This work done is positive as the force acting on the spring is towards right and elongation of the spring is also towards right. So total work done on the spring will be positive and it is 1 by 2 kx square. We know that total external work done on a system is equal to the change in its total mechanical energy. And total mechanical energy of the spring is its kinetic energy plus potential energy. Since spring is massless, so kinetic energy of the spring will remain 0 all the time. So total external work done on the spring will be equal to its change in potential energy. So potential energy of the spring will increase by 1 by 2 kx square. Now suppose the potential energy of a spring in its natural length is 0. So potential energy of the spring will increase by 1 by 2 kx square when it is elongated or compressed by a distance x. Now let us understand potential energy and the nature of equilibrium. Suppose a particle's position and its potential energy graph is given. We know that change in potential energy is equal to negative of work done by the conservative forces. So we can write du is equal to minus fdr or f is equal to minus du by dr. That means conservative force is equal to negative of slope of the curve. There are 3 points of interest: point P, point Q and region Rs. Point P where potential energy is minimum, point Q where potential energy is maximum and region RS where potential energy is constant. At points P and Q and in the region RS, slope of the curve is 0. That means conservative force is equal to 0. Particle will be in the state of equilibrium. There are three types of equilibrium: stable, unstable, and neutral equilibrium. Let us understand them one by one. First one is stable equilibrium. It corresponds to the point where potential energy is minimum. Suppose the particle is at point P. If it is displaced a little bit towards left or towards right, it will keep oscillating about point P till it settles down at P again. This part of the curve is known as potential well. Also, at the location of stable equilibrium, F is equal to minus du by dr is equal to 0, df by dr is less than 0, and d square u upon dr square is greater than 0. Second one is unstable equilibrium. It corresponds to the point where potential energy is maximum. Suppose the particle is at point Q. If it is displaced a little bit towards left or towards right, it will never attain the same position Q again. So it is in the state of unstable equilibrium. At the location of unstable equilibrium, F is equal to minus du by dr is equal to 0, df by dr is greater than 0, and d square u upon dr square is less than 0. Third one is neutral equilibrium. It corresponds to the region where potential energy is constant and force is 0 everywhere. So this is the region where potential energy is constant and this is the region where force is 0. In the region of neutral equilibrium, F is equal to minus du by dr is equal to 0, df by dr is equal to 0, and d square u upon dr square is equal to 0. Now let us talk about power. The rate of doing work is called power delivered. We know that work done by a force F in a small displacement dr is given by the formula dw is equal to F dot dr. So power delivered by the force will be dw by dt, and that is represented by letter capital P. From here dw by dt is equal to F dot dr by dt, and dr by dt is equal to velocity v, because rate of change of displacement is velocity. So power P is equal to F dot v. The SI unit of power is joules per second and it is written as watt. A commonly used unit of power is horsepower. 1 horsepower is equal to 746 watt. Let us solve few questions based on what we have studied so far in this chapter. First question, a man moves on a straight horizontal road with a block of mass 2 kg in hand. If he covers a distance of 40 meter with an acceleration of 0.5 meter per second square, find the work done by the man on the block during the motion. Suppose man and block both are moving in forward direction. Their acceleration is 0.5 meter per second square. So due to this acceleration, a force will be applied on the block in forward direction. Its magnitude is given as mass into acceleration, and that is 1 Newton. Block is getting displaced by 40 meter in the direction of applied force. So applied force and displacement both are in same direction. So work done on the block will be force into displacement, and that is 40 joule. Second question, a force F is equal to 10 plus 0.5x acts on a particle in x direction, where F is in Newton and x in meter. Find the work done by this force during a displacement from x is equal to 0 to x is equal to 2 meter. We know that dw is equal to F dot dx. If we integrate both the sides, we get integration of dw is equal to integration of F dot dx. Here F is a function of x. So we can say w is equal to integration of 10 plus 0.5x dx from x is equal to 0 to x is equal to 2. And that comes out to be equal to 21 joule. Third question, the two blocks in an Atwood machine have masses 2 kg and 3 kg. Find the work done by the gravity during the 4th second after the system is released from rest. This is simple Atwood machine in which this is ideal pulley and this is massless string. The string passes over the pulley. Two ends of the string are connected with masses. In this case, M1 is 2 kg and M2 is 3 kg. System is at rest now. When it is released from rest, this being lighter mass goes up and this being heavier mass goes down. Suppose acceleration of these two blocks is given by A and tension in the string is T. So we can write equation of motion of these two blocks. For this block, equation of motion will be M1A is equal to T minus M1G. And for this block, equation of motion will be M2A is equal to M2G minus T. We can solve these two equations for A and T. A is equal to G by 5 and T is equal to 12G by 5. Next, we will calculate potential energy of two block system at rest. Suppose this is reference line. So potential energy of this block will be 0 and potential energy of this block will be given by M into G into minus H. Since this block is below the reference line, so we will take H as negative. So potential energy of two block system at rest will be minus 3GH. Let's say this is equation number 3. Next, we will calculate displacement of any of these two blocks in fourth second, and that will be given by displacement of any block in 4 seconds minus displacement of same block in 3 seconds. Let's say displacement of this block in 4 seconds is given by S4. So S4 is equal to ut plus half at square. Initially block was at rest, so u is equal to 0. A is equal to G by 5 and T is equal to 4. So S4 is equal to 8G by 5. And displacement of the same block in 3 seconds is given by S3. So S3 is equal to 9G by 10. So displacement of this block in 4th second will be S4 minus S3 and that is 7G by 10. Let's say this is delta S. So delta S is equal to 7G by 10. Delta S is equal to 7G by 10. So 2 kg block will be displaced upwards by 7G by 10 in 4 seconds and 3 kg block will be displaced downwards by 7G by 10 in 4 seconds. So potential energy of the system in 4 seconds will be M1G into delta S plus M2G into minus H minus delta S. Put the value of delta S is equal to 7G by 10. So PE2 is equal to minus 7G square by 10 minus 3GH. So change in potential energy of two block system is equal to delta P is equal to PE2 minus PE1. PE2 is equal to minus 7G square by 10 minus 3GH and PE1 is equal to minus 3GH. So minus 3GH plus 3GH will get cancelled. So delta P is equal to minus 7G square by 10. Take the value of G as 9.8. So delta P is equal to minus 67.23 Joule. So work done by the gravity will be equal to negative of change in potential energy, and that is equal to 67.23 Joule. Fourth question, figure below shows a spring fixed at the bottom end of an incline of inclination 37 degree. A small block of mass 2 kg starts slipping down the incline from a point 4.8 meter away from the spring. The block compresses the spring by 20 centimeter, stops momentarily and then rebounds through a distance of 1 meter up the incline. Find the friction coefficient between the plane and the block, the spring constant of the spring. Take G is equal to 10 meter per second square. This is the figure given. We will consider two cases here, when the block moves down the plane and when the block moves up the plane. When the block moves down the plane, this is FBD of the block. mg is its weight which works vertically downwards. Its component along the plane will be mg sine 37 degree and perpendicular to the plane will be mg cos 37 degree. N is the normal reaction applied by the plane. Since the block is moving downwards, so friction force on it will work up the plane and it is given by mu n, where n is equal to mg cos 37 degree. Net force on the block downwards will be mg sine 37 minus mu n. So F net is equal to mg sine 37 minus mu n is equal to mg cos 37. So it is mg into sine 37 minus mu cos 37. Value of m is given as 2 kg. G we can take 10 meter per second square. Value of sine 37 is 3 by 5 and value of cos 37 is 4 by 5. So F net is equal to 4 into 3 minus 4 mu. This is equation number 1. Work done by this force will be given by force into displacement in the direction of force. We will calculate displacement. Initially, block is 4.8 meter away from the spring and it compresses the spring by 20 centimeter, that is 0.2 meter. So total displacement of the block will be 4.8 meter plus 0.2 meter and that is 5 meter. So work done will be equal to 20 into 3 minus 4 mu. This is equation number 2. Now this work done will be stored as spring's potential energy and that is given by 1 by 2 kx square, where x is amount of compression and k is spring constant. So k is equal to 1000 into 3 minus 4 mu. This is equation number 3. When the block moves up the plane, this is FBD of the block. mg is its weight that works vertically downwards. Its component along the plane is mg sine 37 and perpendicular to the plane is mg cos 37. N is the normal reaction applied by the plane. Since block is moving up the plane, so friction force on it will work down the plane and it is shown by mu n, where n is equal to mg cos 37. So net force on the block will be downwards and it is given by mg sine 37 plus mu n, where n is equal to mg cos 37. Putting the values of m, g, sine 37 and cos 37, we get F net dash is equal to 4 into 3 plus 4 mu. This is equation number 4. Since the spring is compressed, so it will push the block up the plane by equal and opposite force to F net dash. So force applied by the spring will be up the plane and its magnitude will be equal to F net dash. So work done by this force on the block will be F net dash into displacement of the block up the plane and it is given as 1 meter. So W2 is equal to 4 into 3 plus 4 mu. This is equation number 5. Now work done by these forces F net and F net dash will be equal. So we can equate equation number 2 and equation number 5 to get the value of mu as 1 by 2. Now we can put the value of mu in equation number 3 to get the value of k is equal to 1000 Newton per meter. Let us understand circular motion. Consider a particle is moving along this curve in 2D Cartesian coordinate plane. At some point of time, it is at point P. Its position can be represented by polar coordinates r, theta, where r is magnitude of vector OP and theta is the angle that vector OP makes with positive x-axis. At some other point of time, we can represent particle's position by these polar coordinates r, theta. Let us consider 3 cases. Case 1. If only r varies, theta is constant. That means particle will travel in a straight line. Case number 2. If only theta varies and r is constant, that means particle will travel on a circular path. Case number 3. If both r and theta vary, that means particle will neither travel on a straight line nor on a circle. It will travel on some other curve. Let us see angular variables. There are 3 angular variables we will talk about: angular position, angular velocity and angular acceleration. Angular position is represented by theta. Its unit is radian. Angular velocity is represented by omega. Its unit is radian per second. Angular acceleration is represented by alpha. Its unit is radian per second square. They are analogous to position, velocity and acceleration, that is x, v and a in rectilinear motion. Consider a particle is moving on this circular path. It has center at O, O-axis, x-axis. At t is equal to 0, particle was at point P. At t is equal to t, particle was at point Q. And at t is equal to t plus delta t, particle was at point R. At point Q, angular position of the particle is theta. At point R, angular position of the particle is theta plus delta theta, where delta theta is angular displacement of the particle. Its angular velocity omega is rate of change of angular position, which is given by delta theta upon delta t, where limit delta t tends to 0, and that is d theta upon dt. Similarly, angular acceleration is rate of change of angular velocity, and that is d omega by dt, and that is equal to d square theta upon dt square. Let us see what happens when omega is constant and when alpha is constant. Suppose omega is constant, that means d theta upon dt is constant. D theta upon dt is equal to omega, or d theta is equal to omega dt. Let us integrate both sides of this equation within limits. D theta within the limits theta 0 to theta and dt within the limits 0 to t. So integration of d theta from theta 0 to theta will be theta minus theta 0. Since omega is constant, so it can be taken out. So it will be omega into integration of dt from 0 to t, and that will be omega t. So it will be theta is equal to theta 0 plus omega t. We can use this equation when omega is constant. If alpha is constant, that means d omega by dt is constant. D omega by dt is equal to alpha, or d omega is equal to alpha dt. Integrate both sides of the equation within limits. D omega from omega 0 to omega and dt from 0 to t. So left hand side will be omega minus omega 0. Since alpha is constant, so it can be taken out. So right hand side will be alpha into integration of dt from 0 to t, and that will be alpha t. So omega minus omega 0 is equal to alpha t, or omega is equal to omega 0 plus alpha t. Similarly, we can find these two equations. Theta is equal to theta 0 plus omega 0 t plus half alpha t square, and omega square is equal to omega 0 square plus 2 alpha into theta minus theta 0. These three equations are analogous to motion in a straight line. First equation is analogous to v is equal to v0 plus at. Second equation is analogous to x is equal to x0 plus v0t plus half at square. And third equation is analogous to v square is equal to v0 square plus 2a into x minus x0. Let us see proof of these two equations. Proof of this equation first. Angular displacement delta theta is equal to omega average into delta t. Delta theta is theta minus theta 0, and delta t is t minus 0. Omega average is omega 0 plus omega upon 2. Put the value of omega from first equation. Omega is equal to omega 0 plus alpha t. So it will be theta minus theta 0 is equal to omega 0 plus alpha t upon 2 into t. On simplification, it will give theta is equal to theta 0 plus omega 0 t plus half alpha t square. Now let us see proof of third equation. First equation is omega is equal to omega 0 plus alpha t. Square both sides of the equation. So we get omega square is equal to omega 0 square plus alpha square t square plus 2 omega 0 alpha t. Take 2 alpha common in these two terms. So we get 2 alpha into inside the bracket 1 by 2 alpha t square plus omega 0 t. Rearrange the terms, we get omega 0 t plus 1 by 2 alpha t square. Value of omega 0 t plus alpha t square can be put from second equation, and that is equal to theta minus theta 0. So we have got omega square is equal to omega 0 square plus 2 alpha into theta minus theta 0, and that is third equation of circular motion. Suppose the particle travels a small distance delta s on circular path in time interval delta t. Its angular displacement is delta theta. Then from trigonometry we can say that delta s is equal to r into delta theta. If we differentiate both sides of this equation with respect to time, we get delta s upon delta t is equal to r into delta theta upon delta t. Delta s upon delta t is represented by v, which is linear speed of the particle, not linear velocity. Delta theta upon delta t is omega. So we have got this formula, V is equal to R omega. Now, if we differentiate both sides of this equation with respect to time again, we get dV by dt is equal to R into d omega by dt. dV by dt is represented by at, which is tangential acceleration of the particle. D omega by dt is alpha. So we have got another formula, at is equal to R alpha. Let us find out two components of acceleration in circular motion. Suppose a particle is moving on this circular path. At some point of time, it is at point P. Position of this point can be represented by polar coordinates r, theta. Magnitude of vector OP is r, which is radius of the circle. Angular position of point P is theta. Extend OP till A so that PA is a unit vector represented by vector ER. Draw a tangent at point P and extend till P so that PB is another unit vector represented by vector ET. Now we will write vector ER and vector ET. Vector ER is equal to vector PA. It can be written as PA cos theta I plus PA sin theta j. Magnitude of PA is 1. So vector ER is equal to cos theta I plus sin theta j. Similarly, we can write vector ET. Vector ET is equal to vector PB. This angle is 90 minus theta. So we can write vector PB as PB cos 90 minus theta into minus I plus PB sin 90 minus theta into j. So vector ET is equal to minus sin theta I plus cos theta j. Magnitude of PB is 1 as it is a unit vector. Vector R is equal to vector OP. It can be written as R cos theta I plus R sin theta j. If we differentiate both sides of this equation with respect to time, we get velocity of the particle at point P. So velocity V is equal to dr by dt, and that is equal to d by dt of R cos theta I plus R sin theta j. When we differentiate first term with respect to time, we get minus sin theta d theta by dt I. When we differentiate second term with respect to time, we get cos theta d theta by dt j. D theta by dt is omega. So we can take omega common in both the terms and can be taken out. So vector V is equal to r omega into minus sin theta I plus cos theta j. In place of minus sin theta I plus cos theta j, we can write vector Et. So vector V is equal to r omega into vector Et. Vector Et is unit vector. What this means is magnitude of velocity at any point P is equal to r omega, and direction of velocity is along the unit vector Et, which is tangent at that point P. If we differentiate both sides of this equation with respect to time, we will get acceleration of the particle at point P. So acceleration A is equal to dV by dt, and that is equal to r into d by dt of omega into minus sin theta I plus cos theta j. We will get d by dt of omega into minus sin theta I plus cos theta j by applying chain rule. So it will be omega into d by dt of minus sin theta I plus cos theta j plus minus sin theta I plus cos theta j into d omega by dt. Now we can split this into two terms. First term will be r into omega into d by dt of minus sin theta I plus cos theta j will give minus cos theta d theta by dt I minus sin theta d theta by dt j. Second term will be r into d omega by dt into minus sin theta I plus cos theta j. In place of minus sin theta I plus cos theta j, we can write vector Et. So second term will be r into d omega by dt into vector Et. We will simplify first term now. Since both the terms are negative, so negative sign can be taken out. So first term will be minus r omega into. In place of d theta by dt, we can write omega. So inside the bracket will be cos theta into omega I plus sin theta into omega j. Omega can be taken common in both the terms. So it can be taken out. So first term will be minus r omega square into cos theta I plus sin theta j. In place of cos theta I plus sin theta j, we can write vector ER. So first term will be minus r omega square into vector ER. Now we will simplify second term. Second term is r d omega by dt into vector ET. Since r is constant, so it can be taken in. So r d omega by dt can be written as d by dt of r omega. We know that r omega is v. So put v in place of r omega. So second term will be dv by dt into vector et. So acceleration of the particle can be written as minus r omega square into vector er plus dv by dt into vector et. First term is called as radial acceleration. It is represented by ar. And second term is called as tangential acceleration. It is represented by at. Negative sign suggests that it is opposite to unit vector er. Unit vector er is radially outwards. So radial acceleration ar will be inwards towards the center. Magnitude of radial acceleration is r omega square. Put omega is equal to v by r. So magnitude of radial acceleration is v square by r. At is equal to dv by dt. You need to remember these two formulas. There are two components of acceleration of the particle. They are radial acceleration and tangential acceleration. If the speed of the particle v is constant, that means dv by dt is equal to 0. Put dv by dt is equal to 0 in this equation. So particle will have only radial acceleration component, no tangential acceleration. Magnitude of radial acceleration is v square by r. Motion of the particle in this case is called as uniform circular motion. Since particle is having only radial acceleration component, so it will experience a resultant force acting towards the center. This force is called as centripetal force. Magnitude of centripetal force is mv square by r. If particle is having non-uniform circular motion, it will have two non-zero components of acceleration. One is radial acceleration, another is tangential acceleration. Magnitude of resultant acceleration is equal to under root v square by r whole square plus dv by dt whole square. Now let us solve few questions based on what we have learned so far in circular motion. First question, a particle moves in a circle of radius 20 cm at a speed that uniformly increases. If the speed changes from 5 meter per second to 6 meter per second in 2 seconds, find the angular acceleration. From the given information, we can calculate tangential acceleration at. At is equal to change in speed upon duration. So that will be equal to 6 minus 5 upon 2, and that is 1 by 2 meter per second square. Radial or angular acceleration alpha is calculated by the formula alpha is equal to at upon r. At we have calculated as 1 by 2 meter per second square. R is the radius of the circle. It is given as 20 centimeter or 0.2 meter. So alpha is equal to 1 by 2 upon 0.2, and that is 2.5 radian per second square. Second question, a particle moves on a circular path of radius 4 meter. Distance traveled by the particle in time t is given by the equation s is equal to 1 by 3 t cube. Find its speed when tangential and radial accelerations have equal magnitude. We can calculate speed of the particle v by the formula v is equal to ds by dt. It is given that s is equal to 1 by 3 t cube. So ds by dt will give 1 by 3 into 3t square, and that is t square. So speed v is equal to t square. This is equation number 1. We can calculate tangential acceleration at by the formula at is equal to dv by dt. v is equal to t square. So dv by dt will give 2t. That means at is equal to 2t. This is equation number 2. Radial acceleration ar or alpha is equal to v square by r. v is equal to t square. So ar is equal to t to power 4 upon r. This is equation number 3. It is given that magnitude of tangential acceleration and radial accelerations are same. That means 2t is equal to t to power 4 upon 4, or t into 8 minus t cube is equal to 0. That gives either t is equal to 0 or t is equal to 2 seconds. T is equal to 0 means at start v is equal to 0. Speed of the particle is 0. So we will not take t is equal to 0. We will consider only t is equal to 2 seconds. So speed of the particle v is equal to t square. Put t is equal to 2. So v is equal to 4 meter per second. Third question. A particle is moving on a circular path with a constant tangential acceleration. After 2 seconds from the beginning of motion, angle between the total acceleration vector and the radius r becomes 45 degree. What is the angular acceleration of the particle? Suppose the particle is moving on this circular path. OX represents x-axis, O is the center of the circular path. At t is equal to 0 second, particle was at point P, and at t is equal to 2 seconds, particle was at point Q. It is given that at Q, resultant of tangential and radial acceleration vectors makes an angle 45 degree with radius OQ. We know that tangential and radial acceleration vectors make an angle 90 degree with each other. So if their resultant makes an angle 45 degree with radial acceleration vector, that means at Q, magnitude of tangential acceleration and radial acceleration is same. So we can say mod AT is equal to mod AR at point Q. AT is given by dV by dt and AR is given by V square by R, where V is speed of the particle. Put V is equal to R omega. Since R is constant, so it can be taken out. So it will be R into d omega by dt is equal to V square by R. D omega by dt is equal to angular acceleration alpha, which we have to calculate. So R alpha is equal to V square by R, or alpha is equal to V square by R square. Again put V is equal to R omega. So we get alpha is equal to omega square. Suppose this is equation number 1. Since angular acceleration alpha is uniform or constant, we can use this equation omega is equal to omega 0 plus alpha t. Omega 0 is 0 because at t is equal to 0, particle was at rest. So omega is equal to alpha t. Put t is equal to 2 seconds. So we get omega is equal to 2 alpha. Suppose this is equation number 2. Put the value of omega in equation number 1. So we get alpha is equal to 0.25 radian per second squared. Fourth question, a small block of mass 100 gram moves with uniform speed in a horizontal circular groove with vertical side walls of radius 25 cm. If the block takes 2 seconds to complete one round, find the normal contact force by the side wall of the groove. Suppose this is horizontal groove in which a small block of mass m is rotating on a circular path. So when it is rotating, it will experience a centripetal force which is directed towards the center, and that will be equal to normal reaction applied by the wall. So we have to calculate normal reaction applied by the wall, which will be equal to centripetal force, and it is given by mv square by r, where m is the mass of the block, r is radius of the circular path, and v is speed of the block. So speed of the block can be calculated by 2 pi r by t. It is given that it takes 2 seconds to complete one round. So v is equal to 2 pi into r is given as 25 centimeter, that is 0.25 meter, and time is 2 seconds. So v is equal to 0.25 pi meter per second. So normal contact force N is equal to mv square by r. M is 100 gram or 0.1 kg. So it will be 0.1 into v square, that is 0.25 pi square upon r. R is 0.25 meter. So N is equal to 0.25 Newton. Now let us see radius of curvature. Consider a curve PQ. It can be assumed to be made of several small arcs. At any point, there will be a circle whose arc matches with arc at that point. So radius of that circle will be called as radius of curvature at that particular point. If the equation of trajectory of a particle is given, we can find the radius of curvature at a given point by the formula r is equal to 1 plus dy by dx whole square whole to the power 3 by 2 upon mod d square by upon dx square. First, we need to find out dy by dx and d square by dx square at that particular point and then put in this formula. Let us see one question based on this. Equation of trajectory of a particle is given by y is equal to under root 3x minus 2x square, where x and y are in meters. Find the radius of curvature of the path at its peak point. Take g is equal to 10 meter per second square. By just looking at this equation, we can say that this is equation of parabola. Consider a particle is projected with initial velocity u at an angle theta with the horizontal. It reaches a maximum point P and then comes down. So its path is parabolic. Now coordinates of point P will be r by 2 h maximum. That means we have to calculate its range and maximum height. So compare the given equation of trajectory y is equal to root 3x minus 2x square with the equation of trajectory of parabola as y is equal to x tan theta minus gx square upon 2 square cos square theta. So we will get theta is equal to 60 degrees and u is equal to root 10 meter per second. So range r is equal to u square sine 2 theta upon g. Take g is equal to 10 meter per second square. So range r is equal to root 3 by 2 meter. Maximum height is equal to u square sine square theta upon 2g. So maximum height is equal to 3 by 8 meter. So coordinates of P will be r by 2 comma h max, and that will be root 3 by 4 comma 3 by 8. Now given the equation of trajectory is y is equal to root 3x minus 2x square. So dy by dx is equal to root 3 minus 4x. dy by dx at P is equal to, put x is equal to root 3 by 4. So dy by dx at P is equal to 0. That is correct. Slope at the peak point is 0. D square y by dx square from here will be minus 4. That is constant. So radius of curvature at point P will be given by the formula Rp is equal to 1 plus dy by dx whole square whole to the power 3 by 2 upon mod d square y upon dx square. dy by dx is equal to 0. So Rp is equal to 1 plus 0 whole to power 3 by 2 upon mod of minus 4. Mod of minus 4 is 4. So radius of curvature at point P is equal to 1 by 4 and that is 0.25 meter. Now let us understand circular turnings. Consider a vehicle of mass m is moving on this circular road with speed v. This is top view. External forces working on this vehicle are its weight mg that works vertically downwards. Normal reaction applied by the road works vertically upwards. They balance each other. Since the vehicle is taking a turn, so its tires have a tendency to skid radially outwards. So friction force will be applied by the road that will work radially inwards. This is a static friction which is self-adjustable. This provides necessary centripetal force to take a turn. So we can say that friction force Fs is equal to centripetal force mv square by r. Magnitude of this friction force will be equal to μs into n, where n is equal to mg. This is maximum friction force. It cannot be greater than this. So Fs is less than or equal to μs into mg. Put Fs is equal to mv square by r. So we get v square is less than or equal to μs into rg. From this equation, v is less than or equal to under root μs into rg and μs is greater than or equal to v square by rg. This is speed limit. Vehicle cannot have speed more than under root μs into rg. And coefficient of static friction between the tires and the road should be greater than or equal to v square by rg. Let us understand banking of the roads. If the speed of the vehicle is more than this and turns are sharp, as usually happens on hill roads, then friction force alone is not sufficient to stop the tires of the vehicles from skidding. There must be some other provision, and that provision is banking of the roads. In banking of the roads, outer part of the road is somewhat lifted as compared to inner part of the road, so that vehicles moving on the circular path looks little bit tilted towards the center. Let's say theta is the angle of banking. That means road is at an angle theta with the horizontal. In this case, normal reaction applied by the road N will be at an angle theta with the vertical. We can resolve N into two components, vertical and horizontal. Vertical component will be N cos theta, which will be equal to weight of the vehicle mg. Horizontal component N sin theta will provide necessary centripetal force to take a turn. That means N sin theta is equal to mv square by r and N cos theta is equal to mg. If we divide equation 1 by 2, we get tan theta is equal to v square by rg. Here theta depends on speed of the vehicle and radius of the circular path. So v square is equal to rg tan theta, or v is equal to under root rg tan theta. This is speed limit of the vehicle. If speed of the vehicle is little bit more than this, then static friction force, which is self-adjustable, will come into picture. But if the speed is much higher than this, then even a maximum friction force will not be able to stop the skidding of the tires of the vehicle. Now let us understand centrifugal force. Suppose a man is sitting inside a cabin. A heavy box of mass m is also kept in the cabin at a distance r from the center. This cabin is rotating with constant angular velocity omega about z-axis, which is passing through center of the cabin. There is sufficient friction force between the floor of the cabin and the box so that box doesn't slide on the floor while rotating. We will observe motion of this box in inertial and non-inertial reference frames. First, in inertial reference frame. A person who is standing outside of the cabin will see both man and the box rotating with constant angular velocity omega. Forces acting on the box in this case will be its weight that works vertically downwards, normal reaction by the floor which works vertically upwards. Since this box has a tendency to slide radially outwards while rotating, so friction force on it will work radially inwards. This is static friction force, which is self-adjustable. This will provide necessary centripetal force for rotation. So Fs is equal to mr omega square. Let us observe motion of this box in non-inertial reference frame. The person who is sitting inside the cabin will see this box still, not moving, though there is net force acting towards the center. Since this box is not moving, that means there must be a force which is equal in magnitude and opposite in direction, that is working radially outwards. This pseudo force is called as centrifugal force. It is equal in magnitude with centripetal force and opposite in direction. So centrifugal force is equal to minus mr omega square. There are a couple of conclusions we can draw from it. First, if we are working in non-inertial reference frame, then there is a need to imagine pseudo force if the particle is at rest in a uniformly rotating frame. And if we are working in inertial frame, then there is no need to imagine any pseudo force. Let us understand Coriolis forces. We may have to assume other pseudo forces if we are working with non-inertial reference frame. Such pseudo forces are called as Coriolis forces. Coriolis force is perpendicular to velocity of the particle and also perpendicular to axis of rotation of the reference frame. Now let us understand effect of Earth's rotation on apparent weight. Suppose this is Earth, which is rotating with constant angular speed omega about its axis that passes through north-south poles. There is a place P on Earth's surface whose latitude is phi and co-latitude is theta. At this place, there is a room in which a bob is attached with a string and a string is hanged from the ceiling. Bob is in a state of equilibrium. This room itself is rotating on a circular path of radius small r. Capital R is the radius of the Earth. If we see from Earth's reference frame, which itself is rotating with constant angular speed omega, Bob is in the state of equilibrium. That means we can assume there is a pseudo force working on the bob which is radially outwards. This pseudo force is centrifugal force. Its magnitude is mr omega square. Other two forces working on the bob is tension in the spring, that is T, and weight of the bob, that is working towards center of the earth. It is mg. Since bob is in the state of equilibrium, that means there should not be any resultant force working on the bob. So resultant of mg, mr omega square and T should be 0. Alternatively, we can say that resultant of mg and mr omega square should be equal and opposite to T. So let us find out resultant of mg and mr omega square. These are two vectors. Angle between them is 90 degree plus theta, and the resultant is given by under root a square plus b square plus 2ab cos theta. So it will be under root mg whole square plus m small r omega square whole square plus 2mg into mr omega square into cos 90 plus theta. Now, in this right angle triangle, sine theta is equal to small r upon capital R. So, small r is equal to capital R sine theta. Put small r is equal to capital R sine theta here. So, we get resultant is equal to m under root g square minus omega square r sine square theta into 2g minus omega square r. Let us say this part inside under root is equal to g dash. So resultant is equal to mg dash, where g dash is equal to under root g square minus omega square r sine square theta into 2g minus omega square r. G dash will be different at different places on the surface of the earth. It depends on co-latitude theta. Let us consider two cases, when theta is equal to 0 or 180 and when theta is equal to 90 degrees. When theta is equal to 0 or 180, place will be at North Pole or South Pole. So this part will be equal to 0. So G dash is equal to G. That means mg dash is equal to mg. mg dash is called as apparent weight of the body. So in this case, apparent weight is equal to true weight of the body. When theta is equal to 90 degrees, that means at equator, g dash is equal to under root g square minus sine theta is equal to sine 90, that is 1. So g dash is equal to g minus omega square r. Apparent weight of the body mg dash is equal to mg minus m omega square r. So apparent weight of the body will be minimum at equator and maximum at poles. Let us solve a couple of questions based on circular motion. First question, a hemispherical bowl of radius r is rotating about its axis of symmetry, which is kept vertical. A small ball kept in the bowl rotates with the bowl without slipping on its surface. If the surface of the bowl is smooth and the angle made by the radius through the ball with the vertical is alpha, find the angular speed at which bowl is rotating. This is hemispherical bowl, which is rotating about vertical axis with constant angular velocity omega. This is a small ball which keeps on rotating along with the bowl. This is rotating on a circle of radius small r. This angle is given as alpha. Capital R is the radius of the bowl. So in right angle triangle OAP, sin alpha is equal to small r upon capital R, or small r is equal to capital R sin alpha. This is equation number 1. We can draw FBD of the ball. mg is its weight that works vertically downwards. N is the normal reaction applied by the surface of the bow. This angle is alpha. So N can be resolved into two components, one vertical, another horizontal. Vertical component will be N cos alpha and horizontal component will be N sin alpha. Vertical component N cos alpha will balance mg. Horizontal component N sin alpha will provide necessary centripetal force. So N sin alpha is equal to centripetal force mv square by r. Put v is equal to r omega. So N sin alpha is equal to mr omega square. This is equation number 2. And N cos alpha is equal to mg. This is equation number 3. From equation number 1, put small r is equal to capital R sin alpha in equation number 2. So N sin alpha is equal to m capital R sin alpha omega square, or N is equal to m capital R omega square. Put the value of N in equation number 3. So m capital R omega square cos alpha is equal to mg, or omega square is equal to g upon r cos alpha, or omega is equal to under root g upon r cos alpha. Second question, a body weighs 98 Newton on a spring balance at the North Pole. What will be its weight recorded on the same scale if it is shifted to the equator? Use g is equal to gm upon r square, and that is equal to 9.8 meter per second square, and the radius of the earth r is equal to 6400 kilometer. We know that at poles, apparent weight of the body is same as its true weight. So 98 Newton is equal to mg. Given g is equal to 9.8 meter per second square. So mass of the body m is equal to 10 kg. When the body is shifted at equator, apparent weight of the body is equal to mg dash, and that is equal to mg minus mr omega square, where r is radius of the earth and omega is equal to 2 pi by t. T is the time period of the earth, that means the time it takes to make a complete revolution, and that is 24 hours into 60 minutes into 60 seconds. So omega is equal to 7.27 into 10 to power minus 5 radian per second. So mg dash is equal to mg minus mr omega square. R is given as 6400 kilometer, and that is 6400 into 10 to power 3 meter. So mg dash is calculated as 97.662 Newton. Now let us understand circular motion in vertical plane. Suppose a particle of mass m is connected with a light and inextensible string of length r. The string is fixed at point O. Particle is given a horizontal velocity u so that it starts moving on a circular path in vertical plane. At some point of time, it is at point P, so that line OP makes an angle theta with vertical. Point P is at a height h as compared to point A. Our reference line, which is horizontal, passes through point A. First, we will calculate h. H is OA minus OQ. OA is r, length of the string or radius of the circular path. OQ can be calculated from this right angle triangle, and that is r cos theta. So H is equal to r minus r cos theta. This is equation number 1. We can apply conservation of mechanical energy at point A and at point P. At point A, kinetic energy plus potential energy is equal to kinetic energy plus potential energy at point P. Kinetic energy at A is half mu square, and potential energy at A is equal to 0 because point A is passing through the reference line. Kinetic energy at point P is half mv square. Suppose velocity of the particle at P is v. Potential energy of the particle at point P is mg into h. H we have calculated as r into 1 minus cos theta. From this, we get v square is equal to u square minus 2gh. Suppose this is equation number 2. At point P, forces acting on the particle are its weight that works vertically downwards, tension in the string that works towards the center. Component of weight that is along the line OP is mg cos theta. Since particle is moving on a circular path, so net force should work towards center, and that is T minus mg cos theta. That will provide the necessary centripetal force. So T minus mg cos theta is equal to mv square by r. Suppose this is equation number 3. From this equation, T is equal to mv square by r plus mg cos theta. Suppose theta is equal to 0 degrees, that is particle is at A. So tension in the string will be maximum, and it is given by T max is equal to mv square by r plus mg. Put theta is equal to 0 here. When particle is at Q, that is theta is equal to 180 degrees, tension in the string will be minimum, and that is given by T minimum is equal to mv square by r minus mg. Put theta is equal to 180 or pi here. Now let us understand three conditions. Condition of looping, condition of leaving the circle, and condition of oscillation. First, condition of looping. In this condition, particle must be able to complete the loop. That means even at highest point, string should not slack. So tension in the string at highest point should be greater than or equal to 0. Put T is equal to 0 and theta is equal to pi in equation number 3. This gives mg is equal to mv square upon r, or v is greater than or equal to under root gr. Put this value of v in equation number 2. That gives u is greater than or equal to under root 5 gr. That means in order for particle to complete the loop, it should be given a velocity greater than or equal to under root 5 gr. Now from equation number 4, maximum tension in the string that will happen at point A is equal to 6 mg. From equation number 5, minimum tension in the string that will happen at topmost point is equal to 0. Second condition is condition of leaving the circle. If initial velocity given to the particle is less than under root 5 gr, particle will not be able to complete the circle. A string will slack even before the particle reaches at the topmost point. That means tension in the string will be 0. So put T is equal to 0 in equation number 3. This gives cos theta is equal to 2gh minus u square upon gr. Put this value of cos theta in equation number 1. This gives h is equal to u square plus gr upon 3g. Let us say this is height h1. So tension in the string is 0 at height h1. Now put v is equal to 0 in equation number 2. This gives h is equal to u square upon 2g. Let us say this is height h2. Particle will leave the circle if tension in the string is 0, but velocity of the particle at that point is not equal to 0. That means height h1 is less than height h2. So u square plus gr upon 3g is less than u square upon 2g. This gives u is greater than under root 2gr, but u is less than under root 5gr. That means u lies between under root 2gr to under root 5gr. Put u is greater than under root 2gr here. That gives h is greater than or equal to r. So h is greater than or equal to r means theta lies between 90 to 180 degrees. What it means is if initial velocity given to the particle lies between under root 2gr to under root 5gr, particle will leave the circle somewhere between points M and Q. Third condition is condition of oscillation. This condition is just opposite to previous condition. In previous condition, tension in the string was 0, but velocity of the particle at that point was not equal to 0. In this condition, velocity of the particle is 0, but tension in the string at that point is not equal to 0. We had got in previous condition h1 is equal to u square plus gr upon 3g and h2 is equal to u square upon 2g. In previous condition, h1 was less than h2. In this condition, h2 is less than h1. So u square upon 2g is less than u square plus gr upon 3g. This gives u is less than under root 2gr. If we put u less than under root 2gr, here we get h2 is less than or equal to r. That means height is less than or equal to radius of the circular path. So particle will oscillate somewhere in this zone. So if initial velocity given to the particle lies between 0 to under root 2gr, particle will oscillate. Let us summarize our learning. If initial velocity given to the particle lies between 0 to under root 2gr, particle will oscillate between theta 0 to 90 degrees. If initial velocity given to the particle lies between under root 2gr to under root 5gr, particle will leave the circle where theta lies between 90 to 180 degrees. When initial velocity given to the particle is greater than under root 5gr, particle will complete the loop. Let us see three questions based on work, power and energy and circular motion combined. First question, a heavy particle is suspended by a string of length L. The particle is given a horizontal velocity v0. The string becomes slack at some angle and the particle proceeds on a parabola. Find the value of v0 if the particle passes through the point of suspension. Suppose a particle is suspended by a string of length L. O is the point of suspension. Particle is given a horizontal velocity v0 so that it starts traveling on this circular path till point C. At C, the string slacks and particle leaves the circular path and starts traveling on this parabolic path. It is given that particle passes through point of suspension O. We have to calculate the value of v0. First, we will find out velocity of the particle at point C, that is Vc. Suppose line OC makes an angle theta with the vertical. At point C, particle was on circular path. So component of weight that is along CO is mg cos theta. That will provide necessary centripetal force. So we can say that mg cos theta is equal to mvc square upon L, or vc square is equal to gl cos theta. Suppose this is equation number 1. We can apply conservation of mechanical energy at point A and C. So we can say that kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at C. Suppose we take a horizontal line passing through A as reference. So kinetic energy of the particle at point A is half mv0 square and potential energy of the particle is 0. Kinetic energy of the particle at point C is half mvc square and potential energy is m into g into this height, and this height is equal to L plus CD. In this right angle triangle, cos theta is equal to CD upon CO. So this will be L cos theta. So this height will be L plus L cos theta. So potential energy of the particle at C will be mg into L plus L cos theta. This gives V0 square is equal to Vc square plus 2gl into 1 plus cos theta. Suppose this is equation number 2. We can put the value of Vc square from equation 1 to get V0 square is equal to gl into 2 plus 3 cos theta. Suppose this is equation number 3. Now the particle will leave the circular path and start traveling on parabolic path. Suppose we take C as point of reference. Right side and upward we will take positive, left side and downward we will take negative. Horizontal displacement when the particle travels between C to O will be CE or OD, and we will take this as negative. So horizontal displacement OD from this right angle triangle will be minus L sine theta, and velocity component also will be negative, that is Vc cos theta, that is horizontal component of velocity at C. So it will be minus Vc cos theta into t. This is equation number 4. Vertical displacement of the particle between point C and O will be Cd. From this right angle triangle, this will be L cos theta and will be taken negative. So minus L cos theta is equal to vertical component of the velocity will be Vc sin theta. That is Vc sin theta into t minus half gt square. Suppose this is equation number 5. We can put the value of t from here and Vc square from here to simplify it to get cos theta is equal to 1 by root 3. We can put the value of cos theta in equation number 3 to get V0 is equal to under root GL into 2 plus root 3. Second question, figure below shows a smooth track, a part of which is a circle of radius r. A block of mass m is pushed against a spring of spring constant k, fixed at the left end, and is then released. Find the initial compression of the spring so that the block presses the track with a force mg when it reaches the point P, where the radius of the track is horizontal. This is the figure given. Suppose a block of mass m is kept at A. It touches a spring whose other end is fixed to a wall. When the block is pushed towards the left, it compresses the spring by a distance x. When the block is released, the spring pushes the block towards right. It is given that when the block reaches at point P, it pushes the track with a horizontal force mg. We have to calculate the value of x. At point A dash, when the spring is compressed by a distance x, potential energy of the spring is 1 by 2 kx square. When the block is released, let's say its initial velocity is Va dash. So that potential energy of the spring is converted to kinetic energy of the block. So 1 by 2 kx square is equal to 1 by 2 m Va dash square. This gives Va dash square is equal to kx square upon m. Suppose this is equation number 1. At point P, block presses the track with a horizontal force mg. In return, track presses the block towards left, and that is normal reaction by the track. It is nothing but centripetal force. So we can equate horizontal force mg with centripetal force. Suppose at point P, velocity of the block is Vp. So horizontal force mg is equal to centripetal force mvp square upon r. This gives Vp square is equal to gr. Suppose this is equation number 2. We can apply conservation of mechanical energy at point A dash and P. Suppose this is reference line. So kinetic energy of the block at point A dash is equal to half m Va dash square and potential energy is 0. Kinetic energy of the block at point P is 1 by 2 m Vp square and potential energy of the block is mg into this height, and that is radius of the circular path. This gives Va dash square is equal to Vp square plus 2gr. Suppose this is equation number 3. We can put the values of Va dash square and Vp square from equation number 1 and 2. This gives x is equal to under root 3 mg r upon k. Last question. Figure below shows a smooth track which consists of a straight inclined part of length L joining smoothly with the circular part. A particle of mass m is projected up the incline from its bottom. Part A. Find the minimum projection speed V0 for which the particle reaches the top of the track. Part B. Assuming that the projection speed is 2V0 and the block does not lose contact with the track before reaching its top, find the force acting on it when it reaches the top. Part C. Assuming that the projection speed is only slightly greater than V0, where will the block lose contact with the track? This is the figure given. Part A. Suppose the particle starts from point A with projection speed V0. It just reaches the top of the circle and stops there. We can apply conservation of mechanical energy at point A and at point P. At point A, kinetic energy of the particle is half mv0 square. Suppose this is reference line. So potential energy of the particle at point A is 0. Kinetic energy of the particle at point P is 0 because particle stops there. So kinetic energy at P is 0. And potential energy at point P is equal to mg into this height PE. PE is equal to PD plus DE and DE is equal to CB. From this right angle triangle, CB is equal to L sine theta. So P is equal to PD plus L sine theta. We will calculate PD now. PD is equal to PO minus DO. PO is radius of the circle and DO we can figure out from this right angle triangle. First we will figure out angle COD. In this right angle triangle, angle ACB is equal to 90 minus theta. Angle ACO is 90 degree as AC being tangent to the circle. So angle BCO is equal to 90 minus theta. So this angle is theta. Since the angle BCO is theta, so angle COD is also theta. Now this angle is theta. So in this right angle triangle, DO is equal to R cos theta. So PD is equal to R minus R cos theta. So we will put this value here. So half mv0 square is equal to mg into R into 1 minus cos theta plus L sin theta. This gives v0 is equal to under root 2g into R into 1 minus cos theta plus L sin theta. Part B. Now the projection speed is 2v0. That means particle will not stop at P, it will keep moving. Since the particle at P is moving on a circular track, that means net force on it will work towards the center, and that is centripetal force. Suppose velocity of the particle at P is Vp. So net force we have to calculate, and that will be mvp square upon r. Apply conservation of mechanical energy at point A and at P. So kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at P. Kinetic energy of the particle at A is half m into 2v0 whole square. Potential energy is 0 at A because this is reference line. Kinetic energy at point P of the particle will be half m Vp square and potential energy will be mg into this height PE. We have already calculated V0 square and P in part A. So this gives 4mv0 square plus mvp square plus 2mg into P. Suppose this is equation number 1. We have to calculate mvp square upon r, that is net force at point P. So divide both sides by r. That gives mvp square upon r is equal to 4mv0 square minus 2mg into P upon r. Put the values of v0 square and P from part A, and that is v0 square is equal to 2g into r into 1 minus cos theta plus L sin theta, and P is equal to r into 1 minus cos theta plus L sin theta. This gives net force at point P is equal to 6 mg into 1 minus cos theta plus L by r sin theta. Part C. Now the projection speed is slightly more than v0. That means particle will not stop at P, it will keep moving on the circular track. Suppose till point Q. At point Q, particle loses the contact with surface. Suppose line OQ makes an angle alpha with the vertical. We have to calculate the value of alpha. Suppose velocity of the particle at point P is Vp and at point Q is Vq. At point Q, net force will work towards the center, and that is component of weight towards the center, that is mg cos alpha minus n. N is the normal reaction applied by the surface that will work readily outwards. So net force towards the center will be mg cos alpha minus n, and that is equal to centripetal force, that is mvq square upon r. At point Q, particle loses the contact with the surface. That means normal reaction n will be equal to 0. Putting n is equal to 0 in equation 1 will give mg cos alpha is equal to mvq square upon r, or vq square is equal to gr cos alpha. Suppose this is equation number 2. Now we will apply conservation of mechanical energy at point P and Q. So kinetic energy plus potential energy at P is equal to kinetic energy plus potential energy at Q. Kinetic energy of the particle at point P is half m Vp square, and potential energy of the particle at P will be mg into this height. Suppose we are taking line Mn as reference. So this height will be r plus r, that is 2r. Kinetic energy of the particle at point Q is half m Vq square, and potential energy will be mg into this height, and this height is r plus r cos alpha, that is r into 1 plus cos alpha. Now value of Vq square we can put from equation number 2. Vp is negligibly small, so it can be approximated to 0. So we will get the value of cos alpha is equal to 2 by 3, or alpha is equal to cos inverse 2 by 3. Let us solve previous year's JEE questions. Look out for question number 7, that is a tricky one, and last 2 questions. They are JEE advanced questions. So let us start. First question, consider a force F is equal to minus xi plus yj. The work done by this force in moving a particle from point A 1, 0 to B 0, 1 along the line segment is. All quantities are in SI units. These are the options given, and this is figure given. This question was asked in JEE Mains 2020. Given force F is variable in nature. It depends on values of x and y. It can be written as F is equal to Fxi plus Fyj. That is horizontal and vertical components of force F. We know that work done by a force F in moving an object a small distance dr is given by dw is equal to F dot dr. F can be written as Fxi plus Fyj, and dr can be written as dxi plus dyj. Dot product of these two vectors will give fx dx plus fy dy. That means dw is equal to fx ds plus fy dy. Now we can integrate both sides of this equation within limits. We get integration of dw from 0 to w is equal to integration of fx dx from x initial to x final plus integration of fy dy from y initial to y final. It is given that particle is moving from point A to point B. That means x initial is 1, x final is 0, y initial is 0, and y final is 1. Putting lower and upper limits and integrating, we get W is equal to 1 joule. So correct option is option B. Second question, a small bob tied at one end of a thin string of length 1 meter is describing a vertical circle so that the maximum and minimum tension in the string are in the ratio 5:1. The velocity of the bob at the highest position is dash meter per second. Take g is equal to 10 meter per second square. This question was asked in JEE Mains 2021. Suppose this is bob. It is connected to one end of the string. Other end of the string is fixed at point O. This bob is moving on a vertical circle. It is given that ratio of maximum and minimum tension in the string is 5:1. We know that maximum tension in the string will be at lowest point A, and minimum tension in the string will be at topmost point B. Suppose tension in the string at lowest point is T1 and at topmost point is T2. So T1 is to T2 is 5:1, that is given. Suppose velocity of the bob at lowest point is VA and at highest point is VB. We have to calculate the value of VB. At point A, the net force will work towards the center, and that is T1 minus mg, and that will provide necessary centripetal force, that is mva square upon L. So T1 is equal to mva square upon L plus mg. Suppose this is equation number 1. At point B, net force will work towards the center, and that is T2 plus mg. And that will provide necessary centripetal force, and that is mvb square upon L. That gives T2 is equal to mvb square upon L minus mg. Suppose this is equation number 2. Given that T1 by T2 is equal to 5:1. That means mva square upon L plus mg upon mvb square upon L minus mg is 5:1. Put L is equal to 1 meter. It is given as length of the string is 1 meter. So this gives 5 mvb square minus mva square is equal to 6 mg. Suppose this is equation number 3. We have to get the value of Vb. That means we need one more equation. So we can apply conservation of mechanical energy at point A and B. Suppose our reference line, that is horizontal, passes through A. So kinetic energy of the bob at point A is half mva square and potential energy is 0. So at point A, mechanical energy will be half mva square plus 0. At point B, kinetic energy of the bob will be half mvb square and potential energy will be mg into h. H will be L plus L, and that is 2L. So at point B, mechanical energy of the bob will be half mvb square plus 2 mgl. Put L is equal to 1 meter. This gives mva square minus mvb square is equal to 4 mg. Suppose this is equation number 4. We can solve equation number 3 and 4 to get the value of Vb is equal to 5 meter per second. That is our answer. Third question. Two particles A and B are moving on two concentric circles of radii r1 and r2 with equal angular speed omega. At t is equal to 0, their positions and direction of motion is shown in the figure. The relative velocity Va minus Vb at t is equal to pi by 2 omega is given by. These are the options given, and this is the figure given. This question was asked in JEE Mains 2019. At t is equal to 0, first particle is at P and second particle is at Q. Both are on the x-axis. Their angular speed is same. That means at any time t, they will make same angle with the positive x-axis. Magnitude of the angle will be same, but sign will be opposite as the particles are moving in opposite directions. First particle is moving anti-clockwise and second particle is moving clockwise. We will figure out at t is equal to pi by 2 omega the angle they will make with the positive x-axis. Omega by definition is equal to delta theta upon delta t, or delta theta is equal to omega into delta t. Delta theta can be written as theta minus 0 and delta t can be written as t minus 0. At t is equal to 0, theta is equal to 0. It is given. So theta is equal to omega into, put t is equal to pi by 2 omega. So theta is equal to pi by 2. That means at t is equal to pi by 2 omega, first particle will be at p dash and second particle will be at q dash. Their velocity vectors are v and vb. They are in the same directions. So we can write velocity vector va is equal to minus omega r1 I and vb is equal to minus omega r2 I. We are using v is equal to r omega. So Va minus Vb is equal to minus R1 omega I minus of minus R2 omega I, and that is R2 minus R1 into omega I. So option D is correct. Fourth question. The potential energy U of a diatomic molecule is a function dependent on R, interatomic distance, as U is equal to alpha by R2 power 10 minus beta by R2 power 5 minus 3, where alpha and beta are positive constants. The equilibrium distance between two atoms will be 2 alpha by beta to power A by B, where A is equal to dash. This question was asked in JEE Mains 2021. Potential energy function is given as U is equal to alpha by R to power 10 minus beta by R to power 5 minus 3. Magnitude of conservative force is equal to minus du by dr. We can find out du by dr from here. So F is equal to minus 10 alpha into R to power minus 11 plus 5 beta into R to power minus 6. At equilibrium, this force must be equal to 0. That means 10 alpha into R to power minus 11 minus 5 beta into R to power minus 6 is equal to 0. On simplification, this gives R is equal to 2 alpha by beta to power 1 by 5. Compare this R with the given R. So we get A is equal to 1 and B is equal to 5. We have to write the value of A. So the answer is 1. Fifth question. A particle is moving along a circular path with a constant speed of 10 meters per second. What is the magnitude of the change in velocity of the particle when it moves through an angle of 60 degrees around the center of the circle? These are the options given. This question was asked in JEE Mains 2019. Suppose at t is equal to 0, particle is at A, that is along x-axis. Its velocity is VA. After some time, it reaches B, so that angle BOA is 60 degrees. Its velocity at B is VB. We have to find out magnitude of vector VB minus vector VA. It is given that particle is moving with constant speed 10 meters per second. That means magnitude of VA is equal to magnitude of VB is equal to 10 meters per second. We can write vectors VA and VB. Vector VA is equal to magnitude of VA, J, and vector VB is equal to, it can be resolved into two components, horizontal and vertical. So vector VB is equal to minus magnitude of VB cos 30 I plus magnitude of VB sin 30 J. So it can be simplified as VB is equal to magnitude of VB upon 2 into minus root 3I plus J. So vector VB minus vector VA will be equal to magnitude of vector VB upon 2 into minus root 3I plus J minus magnitude of VA J. Put mod VA is equal to mod VB is equal to 10. So VB minus VA can be simplified as minus 5 root 3I minus 5J. Now we will find out the magnitude of VB minus VA, and that is equal to under root minus 5 root 3 whole square plus minus 5 whole square. So that comes out to be equal to 10 meters per second. So option B is correct. Sixth question. A uniform cable of mass M and length L is placed on a horizontal surface such that its 1 by nth part is hanging below the edge of the surface. To lift the hanging part of the cable up to the surface, the work done should be. These are the options given. This question was asked in JEE Mains 2019. Length of the cable is L and the part which is hanging is 1 by nth of L, and that is L by n. Consider a small part of the cable dx which is at a distance x from the edge of the table. Mass of this small part is given by dm is equal to mass per unit length of the cable into length of this small part. So dm is equal to m by L dx. As the cable is getting pulled up, so potential energy of this part will increase. Increase in potential energy is given by du, and du is equal to dm into g into h, and h is equal to x here. So du is equal to m by L into gx dx. We can integrate both sides of this equation within limits. So integration of du from 0 to u is equal to integration of m by L gx dx from 0 to L by n, as the length of hanging part is L by n. So after integration, we get u is equal to mgl upon 2n square. And this is work done on the cable to pull it up completely on the table. So our answer is mgl upon 2n square. So option B is correct. Seventh question. A body of mass 2 kg is driven by an engine delivering a constant power 1 joule per second. The body starts from rest and moves in a straight line. After 9 seconds, the body has moved a distance in meter dash. This question was asked in JEE Mains 2020. Suppose this is the body that is getting driven by this engine. At t is equal to 0, body was at rest. We have to calculate the distance traveled by the body in 9 seconds. Work done by the engine in 9 seconds is given by the formula W is equal to power into time. Power is constant, which is given as 1 joule per second. Time is 9 seconds. So work done by the engine in 9 seconds is 9 joule. Applying work energy theorem, we get change in kinetic energy of the body is equal to work done by the engine. Change in kinetic energy of the body is final kinetic energy minus initial kinetic energy of the body. Final kinetic energy of the body is half mv square. Initial kinetic energy of the body is 0, as the body was at rest initially. M is given as 2 kg. So V is equal to 3 meter per second. That means initially at t is equal to 0, velocity of the body is 0. At t is equal to 9 seconds, velocity of the body is 3 meter per second. Pause for a moment here. What about the acceleration? If acceleration is constant, then we can apply equations of motion in a straight line to calculate the distance traveled by the body in 9 seconds. If acceleration is not constant, then we cannot apply those equations of motion. We need to change our approach. So let us first figure out whether acceleration is constant or not. We know that power is equal to force into velocity. Force can be written as mass into acceleration. So from here, acceleration is equal to power upon mass into velocity. Power is given as constant. Mass is constant, but velocity is not constant. That means acceleration is varying. So we cannot apply equations of motion in a straight line. We need to change our approach. From here, power is equal to m into acceleration can be written as rate of change of velocity, that is dv by dt. So v dv is equal to p upon m into dt. P upon m is constant, as power is given as constant and mass is constant. We can integrate both sides of this equation within limits. So we get integration of v dv from 0 to v is equal to integration of p by m dt from 0 to t. This gives v is equal to under root 2 pt upon m. Now v can be written as dx by dt, rate of change of displacement, and that is equal to under root 2p upon m into root t can be written as t to power 1 by 2. So dx is equal to under root 2p upon m t to power 1 by 2 dt. We can integrate both sides of this equation within limits. So we get integration of dx from 0 to x is equal to integration of root 2p upon m t to power 1 by 2 dt from t is equal to 0 to t is equal to 9. Root 2p by m is constant, as power is given constant 1 joule per second. Mass is constant, that is given as 2 kg. So this gives x is equal to 18 meter. That is our answer. So answer is 18 meters. Eighth question. A block of mass m lying on a smooth horizontal surface is attached to a spring of negligible mass of a spring constant k. The other end of the spring is fixed, as shown in the figure. The block is initially at rest in its equilibrium position. If now the block is pulled with a constant force F, the maximum speed of the block is. These are the options given, and this is the figure given. This question was asked in JEE Mains 2019. Suppose this block is kept on a smooth floor. It is connected to a spring, whose other end is attached to a wall. Now this block is pulled by a horizontal force F, so that it starts moving towards right with some speed. Its speed increases up to a certain extent and then starts decreasing. We have to calculate that maximum speed. When this block is pulled by external force F, spring will be elongated. As a result, spring will apply a force on the block towards left, and that force is equal to minus kx as per Hooke's law. So net force on the block will be F minus kx. Work done by this net force to move the block by a small distance dx is given by dw is equal to F net dot dx. Since force and displacement both are in same direction, so their dot product will give F minus kx into dx. We can integrate both sides of this equation within limits. So we get integration of dw from 0 to w is equal to integration of F minus kx into dx from 0 to x. This gives w is equal to fx minus kx square by 2. Suppose this is equation number 1. We can apply work energy theorem. So change in kinetic energy of the block is equal to work done by the net force on the block. Change in kinetic energy is final kinetic energy minus initial kinetic energy of the block. Final kinetic energy is half mv square. Let's say final velocity of the block is v. Initial kinetic energy of the block is 0 as the block was initially at rest. W is equal to fx minus kx square by 2. This gives v is equal to under root 2 fx minus kx square upon m. Suppose this is equation number 2. For v to be maximum or minimum, dv upon dx should be 0. So finding out dv by dx and equating to 0 gives x is equal to f by k. Put this value of x in equation number 2. That gives v max is equal to f by under root mk. So this is our answer. So option C is correct. Ninth question. A particle of mass m is initially at rest at the origin. It is subjected to a force and starts moving along the x-axis. Its kinetic energy k changes with time as dk by dt is equal to gamma t, where gamma is a positive constant of appropriate dimensions. Which of the following statements is or true? These are the statements given. This question was asked in JEE Advanced 2018. It is given that particle is at origin at t is equal to 0. Also, dk by dt is equal to gamma t. This means dk is equal to gamma t dt. We can integrate both sides of this equation within limits. This gives integration of dk from k initial to k is equal to integration of gamma t dt from 0 to t. This means k minus ki is equal to gamma t square upon 2. K is kinetic energy of the particle at some time t. So it is half mv square. Ki is kinetic energy of the particle at t is equal to 0, and that is 0 because particle is at rest at t is equal to 0. So this gives half mv square is equal to gamma t square upon 2, or v is equal to under root gamma upon m into t. Gamma is given as some positive constant and m is also constant. So v is proportional to t from here. Statement B says the speed of the particle is proportional to time is correct. Again, from this equation, if we do dv by dt, we get under root gamma by m. dv by dt is acceleration of the particle. So acceleration of the particle is equal to under root gamma by m. Force working on the particle is equal to mass into acceleration. So F is equal to under root gamma m. Gamma is constant, m is constant. So force working on the particle is constant. Statement A says the force applied on the particle is constant is also correct. Again, from equation 3, V can be written as dx by dt. So dx by dt is equal to under root gamma by m into t, or dx is equal to under root gamma by m into t dt. We can integrate both sides of this equation within limits. So integration of dx from 0 to x is equal to integration of gamma by m into t dt from 0 to t. This gives x is equal to 1 by 2 under root gamma by m into t square. This part is constant. That means x is proportional to t square. Statement C says the distance of the particle from the origin, that is x, increases linearly with time. This means x is proportional to t. That is incorrect because x is proportional to t square. So this statement is wrong. Let us check statement D. It says the force is conservative. Here force is equal to under root gamma m, which is constant, and we know that work done by a constant force does not depend on the path. So this force is conservative. So this statement also is correct. So correct statements are statement A, B and D. Last question. A student skates up a ramp that makes an angle 30 degrees with the horizontal. He or she starts as shown in the figure at the bottom of the ramp with speed v0 and wants to turn over a semicircular path xyz of radius r, during which he or she reaches a maximum height h at point y from the ground as shown in the figure. Assume that the energy loss is negligible and the force required for this turn at the highest point is provided by his or her weight only. G is the acceleration due to gravity. These are the statements given. We have to figure out which one of them are correct. And this is the figure given. This question was asked in JEE Advanced 2020. Angle of inclination of the ramp is given as 30 degrees. Height of point y is given as h. The student enters this path at point A. Speed of the student at A is given as v0. We can apply conservation of mechanical energy at points A and Y. That means kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at Y. Suppose we take a horizontal line passing through A as reference. Kinetic energy of the student at A is half m v0 square and potential energy of the student at A is 0 because our reference line is passing through A. Kinetic energy of the student at Y is equal to half m vy square. Suppose vy is the velocity of the student at point Y. Potential energy of the student at Y is mg into height of point Y, and that is h. This gives v0 square is equal to vy square plus 2gh. Suppose this is equation number 1. At highest point y, component of weight that is along the ramp is mg sine 30, which will give necessary centripetal force. So mg sine 30 is equal to mvy square upon r. This gives vy square is equal to gr upon 2. Suppose this is equation number 2. We can put the value of vy square in equation number 1 to get v0 square minus 2gh is equal to 1 by 2 gr. Statement A says v0 square minus 2gh is equal to 1 by 2 gr. So statement A is correct. Statement B says v0 square minus 2gh is equal to root 3 by 2 gr. So obviously this is incorrect. Let us check statement C. The centripetal force required at point x and z is 0. A student enters the circular path at point x and leaves at z. We know that in a vertical circle, as the height increases, speed of the particle decreases. So speed of a student at points x and z, which are at the same height, will be more than at y. So centripetal force at points x and z will be more than that at y. So statement C that says the centripetal force required at points x and z is 0 is incorrect. Let us check statement D. The centripetal force required is maximum at points x and z. Since point x is entry point and z is exit point of the circular path, that means speed of the student at points x and z will be maximum. So centripetal force mv square upon r that depends on speed will also be maximum. So statement D is correct. So correct statements are statement A and D. In the next video, we will start chapter number 6, and that is system of particles and rotational motion. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.